Hello dear students, in this video we will have a recap of all the formulae that we have studied in integrals. First we will see integral of a function. Now if we have the derivative of a function f of x as equal to small f of x, then the integral or the primitive or the antiderivative of f of x with respect to x, it is given by integral f of x dx. It is equal to capital F of x. Also we can see that the derivative of f of x plus any constant. The constant can be root 2 or it can be 1.1 or it can be any real number. So if we have the derivative of f of x plus constant equal to this f of x. As a result, what we have is integral f of x dx is equal to capital F of x plus the constant of integration. So we have integral f of x dx is equal to capital F of x plus c. Now we will see the various terms that are here. C is called the constant of integration. This integral is called the sign of integration. Integral f of x dx is equal to f of x plus c. In this, f of x is called the integrand. This capital F of x is called the antiderivative or the primitive of f of x. And f of x dx, it is called the element of integration. So these are the various terms associated with integral f of x dx is equal to capital F of x plus c. And now we will see some of the integrals formula and some standard integrals. So integral x raised to n dx, it is x raised to n plus 1 upon n plus 1 plus c. Then integral 1 into dx, in place of n we have 0 here. So it is x raised to 0 plus 1 upon 0 plus 1, which is x plus c. So integral dx is x. Next integral e raised to x dx, it is equal to e raised to x plus c. Then integral a raised to x dx, it is a raised to x upon log a plus c. Then integral 1 by x dx, it is log mod x plus c. And now we have some more standard integrals here. Integral 1 by root of x square plus a square dx, it is equal to log mod x plus root of x square plus a square plus c. Next we have integral 1 by root of x square minus a square dx. It is log mod x plus root of x square minus a square plus c. Now let us continue with the formula for some more standard integrals. Next we have integral root of x square plus a square dx. It is x by 2 root of x square plus a square plus a square by 2 log mod x plus root of x square plus a square plus c. Next we have integral x square minus a square dx. It is x by 2 root of x square minus a square minus a square by 2 log mod x plus root of x square minus a square plus c. And next we have integral 1 by x square minus a square dx. It is 1 by 2a log mod x minus a upon x plus a plus c. Then we have integral 1 by a square minus x square dx. It is equal to 1 by 2a log mod a plus x upon a minus x plus c. So these are the formula for some of the standard integrals. Now moving on to various methods of integration. We have studied three methods. The first one is integration by substitution. Next is integration using partial fractions. And next is integration by parts. Now we will see each method one by one. First is integration by substitution. If in the integrand we have root of f of x, then the substitution that we have to make is f of x is equal to t square. Then if in the integrand we have log x, then we have to put log x equal to t or x is equal to e raised to t. And then if the integrand is the composite function of f and g, that is f of g of x. If this is the case, then the substitution that should be made is g of x equal to t. Next, if the integrand is of the form f of x the whole raised to m by n, then we have to put f of x equal to t raised to n. That is what is in the denominator of the fraction that should be taken as the power of t. And if we have integral f of x dx is equal to capital F of x plus c, then integral f of ax plus b dx, it will be 1 by a capital F of ax plus b plus c. Moving on, next we have integration by partial fractions. If we have to integrate a rational function is a function which is defined as the ratio of two polynomials which is of the form p of x upon q of x. If we have such a function, then we have to use integration by partial fractions. Here p of x and q of x are polynomial in x and q of x is not equal to 0. Under this rational functions, we have two types. One is improper rational function and the other one is proper rational function. If the rational function is a proper rational function, that is if the degree of the numerator is less than the degree of the denominator. If we have x upon x plus 1 into x plus 2. Here the degree of the numerator is 1 and the degree of the denominator is 2. It is x by x square plus 3x plus 2. So such a rational function is called a proper rational function. If a rational function is a proper rational function and we have to integrate such a function, then we can proceed with integration by partial fractions. If the rational function is an improper rational function, that is if the degree of the numerator is more than the degree of the denominator. Say for example, x cube upon x square plus 2. Here the degree of the numerator is 3 and the denominator is 2. In this case, we have to convert this improper rational function to a proper rational function and then we have to proceed with integration by partial fractions. We have to perform long division to convert this. So if we use long division where we can divide p of x by the denominator q of x, then we will have p of x is equal to t of x into q of x plus r of x, where t of x is the quotient and r of x is the remainder. Now if we divide p of x upon q of x, then here q of x will cancel. We are left with t of x plus r of x upon q of x. Now this becomes a proper rational function, and for this proper rational function we can perform integration by partial fractions. And here this is usually going to be an algebraic function, so we know how to integrate an algebraic function. So this is how we have to proceed when there is an improper rational function. And now moving on to the partial fraction decomposition that has to be made for different types of rational function. The first one, if the rational function is of the form px plus q upon x plus a into x plus b, then the corresponding partial fraction decomposition is a by x plus a plus b by x plus b. Next, if the rational function is of the form px square plus qx plus c upon x plus a into x plus b into x plus c, then the corresponding partial fraction decomposition is a by x plus a plus b by x plus b plus c by x plus c. And next, if it is of the form px plus q upon x plus a the whole square, then the partial fractions are a by x plus a plus b by x plus a the whole square. And next, if we have the rational function as px square plus qx plus c upon x plus a into x plus b the whole square, then the corresponding partial fractions will be a by x plus a plus b by x plus b plus c by x plus b the whole square. And finally, if we have a rational function of the form px square plus qx plus a upon x plus a into x square plus b, then the partial fraction decomposition consists of a by x plus a plus bx plus c upon x square plus b. So we can equate these two and we can compare the coefficients of x, x square and the constant term and find the values of a, b and c. Now say for example, if we want to find the integral of integral 3x plus 2 upon x plus 1 into x plus 2 dx. Let us take this as I. Then here we can use integration by partial fractions. So here this we can write it as a by x plus 1 plus b by x plus 2. So from this we get this is equal to a into x plus 2 plus b into x plus 1 upon x plus 1 into x plus 2. Now these two will cancel. So we get the numerator as 3x plus 2 is equal to a into x plus 2 plus b into x plus 1. Now we can equate the coefficient of x and constant terms. Here we will have ax plus 2a plus bx plus b. In the left hand side the coefficient of x is 3 and in the right hand side the coefficient of x is a plus b. So we will have a plus b equal to 3 and then the constant term on the left hand side is 2 and on the right hand side it is 2a plus b. So it is 2a plus b. This is equal to 2. Now we can solve these two equations and we can find a and b. If we solve these two equations, we get a equal to minus 1 and b equal to 4. So we have taken this integrand as a by x plus 1 plus b by x plus 2. So the given integral, it becomes minus integral 1 by x plus 1 dx plus 4 integral 1 by x plus 2 dx. So in place of this, we can write a by x plus 1 plus b by x plus 2. A we got minus 1 and b we got 4. Now this we can integrate very easily. It is minus log mod x plus 1 plus 4 log mod x plus 2 plus c. So this is how we can use integration by partial fractions to integrate functions of this form, that is to integrate rational functions, proper rational functions. Next, moving on to integration by parts. When we have to integrate product of two functions, that is if we have an integral of the form integral f of x, g of x, dx, then we can integrate such functions using integration by parts by taking f of x as the first function and g of x as the second function. We can integrate this as f of x into integral g of x dx minus integral f dash of x to integral g of x dx plus c. So this is how we can find the integral of product of two functions. So we can use this formula The use of this formula is called integration by parts. Now which function should be taken first and which function should be taken second? It is based on the rule given by I late. Here I represents inverse trigonometric functions, L represents logarithmic functions, A represents algebraic functions, T represents trigonometric functions, and E represents exponential functions. So we can use this order I late so that we will be able to take the first function in this order and the second function which comes after this. Say for example, if we want to integrate integral x log x dx. Here according to this order, we can take the first function as log x. So log x can be taken as f of x and x is an algebraic function. Here x can be taken as the second function which is g of x, and we can integrate by parts. Now let us take another example, say x square e raised to x dx. So in this order, we can take the first function as the algebraic function which is x square and the second function as exponential function e raised to x. So we can take f of x as x square and g of x as e raised to x, and we can use integration by parts, use this formula, and we can find the integral of this function. So this is with respect to integration by parts. If we have integral of the form e raised to x into f of x plus f dash of x dx, we have an integral of this form, then the integral of such a function, it is equal to e raised to x into f of x plus c. So if you are able to write the given integrand of the form e raised to x into f of x plus f dash of x, then we can find the integral of such a function as e raised to x into f of x plus c. Say for example, if we have integral e raised to x into log x plus 1 by x dx. Here we can see that f of x is log x and f dash of x is 1 by x. So the integral of this function, it is equal to e raised to x log x plus c. So like this we can write this directly. And now moving on to definite integral. Definite integral, it is denoted by integral a to b f of x dx, where a is called the lower limit of the integral and b is called the upper limit of the integral. Now what is this integral a to b f of x dx? This integral a to b f of x dx, it is nothing but it is the area bounded by the curve y equal to f of x, the ordinates x equal to a, x equal to b, and the x-axis. So this entire area, it is given by integral a to b f of x dx. So it is the area bounded by y equal to f of x, then the ordinates x is equal to a, x is equal to b, and x-axis. Now if we have a point in this is a and this is b. Now if we have a point, say x, in this closed interval a comma b, let x belongs to closed interval a comma b. Then integral a to x f of x dx, it is the area which is bounded by this part. Now here we can see that the area of this region depends on the value of x. Hence, we have the area function, and this area function is given by integral a to x f of x dx because it is a function of x. So, the area function a of x is equal to integral a to x f of x dx, where a less than or equal to x less than or equal to b. So, this is with respect to area function, and this is how we can find the area under the curve. Because definite integral, it is the area which is bounded by the curve, the lines x is equal to a, x is equal to b, and the x-axis. So, in general, the area function a of x is given by integral a to x f of x dx, where x is any point in the interval a comma b. And now moving on to the first fundamental theorem of integral calculus. Let f be a continuous function on the closed interval a comma b, and let a of x be the area function. Then we have a dash of x, it is equal to f of x, where x belongs to closed interval a comma b. So, if a of x is the area function, then the derivative of a of x, it is equal to f of x. And now moving on to the second fundamental theorem of calculus. Let f be a continuous function defined on the closed interval a comma b, and capital F of x be an antiderivative of f of x. Then we have integral a to b f of x dx, it is equal to the antiderivative of f of x with the limits a to b. This is equal to f of b minus f of a. Here in the antiderivative, we have to substitute the upper limit first, f of b minus the lower limit in place of x to obtain the value of integral a to b f of x dx. So, this definite integral a to b f of x dx, it has a value, a specific value. Now, moving on to the properties of definite integral. Now, we will see the various properties of definite integral. The first property is integral a to b f of x dx, it is equal to integral a to b f of t dt. That is, the value of the definite integral is independent of the variable x. Now, moving on to the second property. Second property is integral a to b f of x dx, it is equal to negative integral b to a f of x dx. So, here if we change the limits, if the lower limit becomes the upper limit, and if the upper limit becomes the lower limit, then the sign of the definite integral changes. So, it becomes negative integral b to a f of x dx. Next, we have the third property, integral a to b f of x dx, it is equal to integral a to c f of x dx plus integral c to b f of x dx, where a less than c less than b. So, if c is any point in a comma b, open interval a comma b, then we have integral a to b f of x dx is equal to integral a to c f of x dx plus integral c to b f of x dx. Now, this is very useful in finding the integral of modulus function. Usually, integral of modulus function can be expected for 4 marks. Say for example, integral minus 1 to 1 mod x dx. We can write this as integral minus 1 to 0 mod x dx plus integral 0 to 1 mod x dx. Now, in this interval, integral minus 1 to 0 mod x is negative x. So, it is integral minus 1 to 0 negative x dx plus integral 0 to 1. In the interval 0 to 1, mod x is positive. Positive x dx. And then we can proceed with finding the value. So this is how the third property is very useful in finding the value of the definite integral of modulus functions. Now moving on to the fourth property. The fourth property, integral a to b f of x dx, it is equal to integral a to b f of a plus b minus x dx. Here in place of x we can replace with a plus b minus x. The definite integral of those two are going to be the same. The fifth property, integral 0 to a f of x dx, it is equal to integral 0 to a f of a minus x dx. So if we have to find the value of definite integral of the form integral 0 to a f of x dx, then we can replace x by a minus x and then we can find the definite integral. Now we have the sixth property, integral 0 to 2a f of x dx, it is equal to integral 0 to a f of x dx plus integral 0 to a f of 2a minus x dx. This is the sixth property. And then we have the seventh property which is based on this property. The seventh property is integral 0 to 2a f of x dx. It is twice integral 0 to a f of x dx if f of 2a minus x equal to f of x. So here if f of 2a minus x is equal to f of x, then we have this integral. It is equal to twice integral 0 to a f of x dx, and it is equal to 0 if f of 2a minus x equal to negative f of x. So if this is equal to negative f of x, then this becomes 0. And then we have the last property. The last property is integral minus a to a f of x dx. It is equal to 2 times integral 0 to a f of x dx if f of x is even, and it is equal to 0 if f of x is odd. A function is said to be even if f of minus x is equal to f of x. Say for example x square, if we take f of x as x square, then f of minus x will be minus x the whole square, which is again equal to x square. So x square is an even function. On the other hand, if we take say x cube, then here f of minus x will be minus x the whole cube, which is negative f of x. So if f of negative x is equal to negative f of x, then we call such a function as an odd function. This is an odd function. Whereas if f of negative x is equal to f of x, then it is called an even function. So if a function is even, integral minus a to a f of x dx is equal to 2 times integral 0 to a f of x dx, and if f of x is odd, this is equal to 0. And now moving on, next we have the cost and revenue function. We have said it in derivatives. The derivative of the cost function is the marginal cost. So the cost function can be calculated as integral of the marginal cost function. So the cost function c of x, it is equal to the marginal cost function dx, where mc is the marginal cost. Then we have the revenue function. In derivatives, we have studied the derivative of revenue function is the marginal revenue function. So the revenue function is given by integral of marginal revenue function dx, where MR is the marginal revenue. So this is with respect to cost and revenue function. The last topic in integrals is consumer surplus and producer's surplus. The consumer surplus, it is given by integral 0 to x naught f of x dx minus p naught x naught. In the question, either p naught or x naught will be given. So if p naught is given, then we have to find x naught, which is based on the demand function which is given in the question. And then we can find the consumer surplus using this relation. Here f of x is the demand curve. The producer surplus, it is given by p naught x naught minus integral 0 to x naught g of x dx. Again, if in the question p naught is given, then we can find x naught using the supply curve which is given in the question. Here g of x is the supply curve, and then after that we can find the producer surplus using this relation. Here g of x is the supply curve. Next we have the equilibrium price. The equilibrium price is the price where the amount of product that the consumers want to buy, that is the quantity demanded, is equal to the quantity supplied. And the associated quantity, the associated amount, it is called the equilibrium quantity. So these are the various formulae that we have studied in integrals. I hope this video was useful for you. If you are visiting my channel for first time, please subscribe. Thank you for watching.